Hello, this is Hardcracker. So the knowledge is like an ocean of scattered dots, and let's learn them by cracking similar problems together and connect those dots. Hopefully in this way, eventually we will further build up our own brain map to solve problems with the applicable and optimal solutions. So I will use the series of topics on LeetCode called the best time to buy and sell stock to demonstrate why dynamic programming can be used for this type of problem and how it can be used in the top-down and bottom-up approaches. Specifically, through this video, I want to demonstrate how these two approaches are different from each other, or are they really different from each other? Learning is always fun. Let's connect some dots today. I think a common challenge for people who first started learning dynamic programming is that they tend to jump directly to look for the transition function. So finding the transition function can be very experience based, and people sometimes say that finding the transition function can be the art of the dynamic programming. So as what it sounds, if something really becomes an art, it will be challenging for an ordinary person like me to fully grasp. So in my mind, a transition function will become apparent in the following scenario. If you have seen the problem before, if the question is really simple, maybe you are simply a genius or you are really good at dynamic programming after extensive practices. I think in reality, for a brand new problem, first we need to determine if it can be solved with dynamic programming and if it can and how we can solve it. I think the key is really to draw the recurrent tree for a dynamic programming problem. I like to emphasize all the important messages I like to convey by repeating 3 times. So it's really helpful to draw the recurrent tree, draw the recurrent tree, and draw the recurrent tree. So to fully demystify dynamic programming, there are 3 steps. Step 1, on the concept level, we need to know the 2 key attributes for a problem to be solved using dynamic programming. I think the first one is optimal substructure, which means that you can construct an ultimate optimal solution from optimal solutions of a sub-problem. And the second attribute is the overlapping subproblems. Basically means that you are repeating solving the same problem over and over again. And step 2 is in order to see if a problem has these 2 key attributes, you need to draw the recurrent tree. Once you draw the recurrent tree, it will be apparent if this problem has these 2 key attributes. And the last step is basically if it has these 2 key attributes, and you can just try to use both the top-down and bottom-up dynamic programming approaches for practice. And we will get there later. So let's use the famous Fibonacci number as an example. Basically for Fibonacci number, the number at index 0 is 0, at index 1 is 1, and the number at index n equals to the number at index n minus 1 plus the number at the index of n minus plus 2. So in order to get as 5, we need to get f3 plus f4, and in order to get f3, we need to get f1 plus f2, and in order to get f4, we need to get f2 plus f3. So by drawing the recurrent tree, and clearly we can see that the ultimate optimal solution can be constructed from the optimal solutions of a subproblem, and at the same time we are just repeating solving the same problem over and over again, for example for f3, for f2, and for these f1 and f0. So what we need to do for someone who started learning dynamic programming is always draw the recurrent tree unless you are very comfortable to draw it in your head. And please don't jump directly to look for the transition function. You may not see it for complex or new problems. And please don't memorize a template. I think a template may only work for some problems that have been selected, even including the template I gave you in this video. So let's talk about the top-down dynamic programming and bottom-up dynamic programming. and where do these directions come from? What is exactly top down? What is exactly bottom up? And both the top down and bottom up information processing approaches to get the final answer from the known information. So the direction is really the order of getting the final answer relative to the known information, which are the base cases in the recurrent tree. So the top-down approach is basically recurrent plus memoization. So at first level, I want to briefly talk about what is memoization, because in the recurrent tree, you are repeating solving the same problem over and over again. So the memoization is basically you build up a table or a notebook, and then you record the answer to the sub-problem you solve at the first time. So the next time when you see the sub-problem, you can just use the answer from the notebook or from the memo or from the table. So you don't have to keep repeating solving the same problem again and again. And then in the top-down approach, so basically it starts from the final answer you need, and then you recursively call the sub-problems until you hit the base cases with the information you already know. And this is all based on a recurrent stack. And when you recursively calling a recurrent stack will be stacked together automatically by the algorithm. And then once you hit the base cases, the values will be returned and back calculate all the sub-problems until you reach the final answer you need. And during this process, the recurrent stack will start popping. So basically, the recurrent stack will pop to help you automatically build the table or the notebook you need. But instead, in the bottom-up tabulation approach, basically, you will not use a recurrent, and there will be no recurrent stack. Instead, you will just rely on the transition function. You start from the base cases you already know, and you just directly keep building a table to the sub-problems until you reach the final answer you need. So the similarities between the top-down and the bottom-up approach is basically you need a table, you need a memo to help you record the answers to the sub-problems you already solved. And you also need to rely on the known information in the base cases to help you reach to the final answer you need. But the difference is in the top-down approach, it will use recurrent. So basically, by using the recurrent, you will start from the final answer by recursively calling the sub-problems until you hit the base cases, and then the base cases, the recurrent stack will start popping, and the base and the value and the popping of the recurrent stack will help you automatically build the table. But instead, in the bottom-up approach, basically, you will build the table by yourself, starting from the basic cases by using the transition function. There are in total 6 different problems in the best time to buy and sell stock series on LeetCode. Basically, for all these problems, you will give an array called prices and with the stock price at different day. And you may not engage in multiple transactions simultaneously. You must sell the stock before you buy again, which means that basically the number of stock in your account can only be 0 or 1. And the final ask is to ask you what will the max profit be. So there are 6 different problems, and the number 188, the problem 4 is basically the generic form, and the restriction will be you can perform at most k transactions. And the other problems are kind of like special cases of this generic problem. For example, for 1-to-1, you will have at most 1 transaction. For 1-to-2, you will have a limited number of transactions. And for 1-to-3, you will perform at most 2 transactions. and for 309 with the cooldown, you need to take a cooldown after time you sell the stock, which means that if you sell the stock and then in the next day you can't buy the stock again. And then for 714 with the transaction fee, basically every time you sell the stock you have to pay the transaction fee. And for all these problems, they can be solved with dynamic programming. And we can see that from the recurrent tree that because all these problems have those two attributes for a problem to be solved with dynamic programming. So whenever we have a recurrent tree, we will need parameters to help us track the state, basically where we are in the recurrent tree. And from both the top-down and bottom-up perspective, we need parameters to help us track the state where we are. And for stock series problem, and we will have these three parameters to help us track where we are. The first parameter will be the day. For a zero indexed array, basically for the day we will have from 0 to n-1. And the second parameter will be the maximum allowable number of transactions. Problem 4, the generic form will give the limit as k, and it will start from 0 to k. And the third parameter will be the number of stocks in the account, because in the problem it won't allow you to buy another stock until you sell the stock in your account. So the number of stock in the account will be either 0 or 1. And the impact of the intuition of these parameters basically when the stock in the account is 0, which means that we have no stock in our account, we can either rest or buy a stock. And when the number of stock is 1, which means that we have 1 stock in our account, we can either rest or sell the stock. So I think one thing I really want to bring up is the key here is really to be consistent with how your parameters are defined. So I'm trying to say that we need to be consistent with how day is counted. For example, if it is counted at the beginning of a day or it's counted at the end of the day. And in our example, it will be counted at the end of the day. And also try to be consistent with how the transaction is counted. Basically, it means that we need to be consistent if a transaction is counted after a buy or after a sell. So basically, in our example, it will be counted after each sell. And I tried different combinations. I think the different combination work, and you just need to be consistent and not confuse yourself within your own approach or with other people's approaches. So how are we going to define the state with parameters? Basically, how we are going to use the parameters to track where we are on the recurrent tree in the top-down approach, and also where we are in building the table in the bottom-up approach. So like we mentioned, we wanted to be consistent with how our parameters are defined. At the same time, we want to be consistent with how a state can be defined with the parameters. So we can either define the state or where we are, the FIJP with all three parameters as the optimal answer at the end of ith day with J transactions and P stocks. Or we can also define FIJP as the optimal answer at the beginning of I day with J transactions and P stocks. So believe it or not, both work. So I think we just need to be consistent how our state or where we are is defined with parameters. So let's use the first scenario, how we define the state with the parameters. We define the FIJP as the optimal solution we can build by the end of the I day with J transactions with P stocks in the account. And let's just take another look at the base cases and transition function. So basically the ultimate result we want to get is the optimal solution we will have at the end of the last day with K transactions with 0 stocks in our account. Basically we want to sell the stock so that we can get the optimal gain. We want the optimal result at the end, and the base cases will be at the very beginning. and some base cases will be at the end of the first day. So no matter how many transactions you made, if you have 0 stocks, it will be 0. If you have 1 stock, it will be the minus stock price of the first day. And the other base cases will be when j equals to 0 and I is larger than 0, which is basically you did not make a full transaction, but you may or may not buy the stock already. So remember that we define our transaction at the end of the sale. So basically, transaction number is only increased at the end of the sale. So when j equals to 0, you may already buy 1 stock or you may not buy any stock. So if you don't buy any stock, it equals to 0. And if you already buy a stock, depending on if you buy it on 8th day or any day earlier, it will be the larger one between the minus today's stock price and also the optimal solution from the previous day. And then for the transition function, it's basically when you have no stock by the end of 8th day is a result of either rest or sell. It's based on the optimal solution from the previous day. You can either rest or sell the stock. If you have a stock at the end of the 8th day, it's based on the optimal solution from the previous day. You can either rest or buy, and you take the larger value between the rest and buy on the 8th day. As you can see that the big O for the time will be O n times k, and for the space complexity, the big O will also be O n times k. And this is because while you're trying to build up the memo or the table, you are basically iterated through all the n's and k's, and then you will have the time complexity n times k. And for the the third parameter, it will be either 0 or 1 times 2. So when you calculate the big O, it doesn't really matter here. So this is the recurrent tree for the top-down dynamic programming for stock problems. From this recurrent tree, we can see that the optimal solution to the final answer we want will be constructed from the optimal solutions to the sub-problems, and at the same time we can see that we have repeating sub-problems here, and we also have repeating sub-problems here. We also have repeating sub-problems here. So from this recurrent tree, and we can see that this problem can be solved with dynamic programming by having those two attributes. So let's look at the top-down dynamic programming for the stock problems if we use the stock problem for the generic form as an example. And we can see that our goal here is to get the fn-1 k0, which is the optimal solution at the end of the last day with k transactions and no stock in our account. And for the top-down approach, again, we have our ultimate goal, and we will try to recursively call all the other sub-problems until they hit the base cases. And in the recurrent, we will try to call the other sub-problems with these recurrent relation, which is basically the same as the transition functions we just introduced. During the recursive calling, we will have a recursion stack, and then once they hit the base cases, we just talk about we have the known information, and then the recursion stack will start popping. The result will be returned to all the sub-problems to back calculate all the sub-problems until we reach the final result we want. And when the recurrence stack pops, actually it will automatically help us to build the table and the memo to keep track of the answers to all the subproblems. Now let's take a look at the bottom-up dynamic programming for stock problems. And again, we have almost the identical recurrent tree, even though in the bottom-up approach, we will not use the recurrent, and we will directly build from the base cases to get the final optimal solution. But just from this recurrent tree, you can see that the final optimal solution can be built by the optimal solution of the subproblems, attribute number 1. And then we have attribute number 2. We definitely see repeating subproblems. We definitely see repeating subproblems. We see repeating subproblems here. We see repeating subproblems here. We also see repeating subproblems here. So by having these two attributes, clearly we can solve this problem using the dynamic programming. And in the bottom-up approach, and our ultimate goal is to get dpn-1 k0, which is the optimal result we can build at the end of the last day with k transactions and 0 stock. And when we use the parameters to track where we are when we build the dynamic programming table or memo, the dpijp means that the optimal solution at the end of I day with Z transactions and P stock in our account. So for the bottom-up approach, we start from the base cases with all the information we know, and then per the transaction function we talked about, and then we start building from bottom to up to build the solutions to all the sub problems until we get the final answer, the final optimal solution. As you can see now, the top-down approach and bottom-up approach are actually pretty similar. For top-down approach, right? And in the recurrent tree, you recursively call all the subproblems, you hit the base cases, and then the recurrent stack pops, and you will automatically build up the table or the memo you need to track all the subproblems. But in the bottom-up approach, you start from the subproblems and you directly build the table tracking all the subproblems until you hit the final result. So they are actually very similar. I think the difference is just in the top-down, it uses the recurrent stack. And this is the code for the top-down dynamic programming. From this code, and you can easily see how the top-down dynamic programming works. So this is written in Java, and I would like to just have some global variables, so I don't need to put all these into the parameters when I write the recurrent function. Basically, I want to build up a memo to track all the answers to the subproblems, and our ultimate goal is to get the result at the end of the last day with k transactions and the 0 stock in our account. This is the recurrent function. There's already a value in the memo. You just use the value directly, so you don't need to repeat solving the same problem again. And these are the base cases. Once you hit the base case, you will get the information you already know. These are the recurrent relations for IJP. So again, depending on if you have stock in your account at the end of the 8th day, the optimal solution will based on the optimal solution from the previous day, right? From the previous day. And if you don't have stock, it means that you either rest today or sell the stock today. Or if you have If you have one stock, it means that you either rest today or you bought the stock today. So that's pretty much the top-down dynamic programming code. And similarly, this is the code for the bottom-up dynamic programming for stock problems. And in the bottom-up approach, you will not use the recurrent function. You will directly build up your memo or table to track the optimal solutions to the sub problems. These are the base cases. You have all these information you already know, and then you will start building directly the table and the memo you need. These are the transition functions we talked before. Depending on if you have no stock or one stock at the end of each day, your optimal solution will based on the optimal solution from the previous day. If you have no stock, you either rest today or sold the stock today. If you have one stock by the end of the day, you either rested from a previous day or you bought the stock today. And then you will return the optimal solution at the end of the last day with key transactions and no stock in your account. So here's a summary of all the variations for the best time to buy and sell stocks. And we already talked about this number 4 is the generic form with at most k transactions. As you can see that when you iterate through the transaction number, you have j smaller than or equal to k. Stock 1 problem is basically you can have at most one transaction. Here you will have smaller than or equal to 1, which is basically smaller than 2. And for the stock problem number 3, you have at most 2 transactions. So here you will have smaller than or equal to 2. And then for the stock problem number 2, it basically means that you don't have any restriction on the numbers of transactions you can make. And because there's no restriction here, we don't really need to track the number of transactions because there's no really limitations on this. So you don't need to track the second parameter. You only need to track on day and the number of stock in your account. And then for the problem, I believe 6, and you will have a transaction fee, which means that after each sale, you need to pay a fee. But there's no limitation number of transactions. So again, you don't need to keep track of the number of transactions. You only need to track the parameters of days and the number of stocks in our account, and just to make sure that every time you sell stock, you paid the fee. So I want to talk about the buy and sell stock problem number 5 with cooldown separately from all the other problems, because this problem is slightly different regarding the parameters we are going to use track the state where we are in the recurrent tree or where we are building the DP table. So the parameters we are going to use for the stock buying and selling with the cooldown is different from the other problems. So we have the similar thought process here, but we will not have a parameter of the transaction because there's no limitation of the number of transactions, but instead we will have additional parameter called cooldown. So we will still have the parameter of day. We will still have the parameter of number of stock in our account, and we will have the third parameter called cooldown. When it's 0, it means that we can't buy, it's in cooldown phase. When it equals to 1, it means that we can buy, it's not in cooldown phase. So our final goal is to get the maximum value between fn-1, 0, 0 and fn-1, 0, 1. So why is that? Because we ultimately want to get the optimal solution at the end of the last day with no 0 stocks in our account. But we may either in the cooldown or not in the cooldown at the last day. So for the last parameter, it may be either 0 or 1. We don't know. It depending on if we sell the stock on the last day or the day before the second to the last day or any days earlier. So we don't know. So that's why we will take the maximum between these two. For the base cases, so we will try to get the optimal solution by the end of the first day. And then it's just the different combinations between the number of stock and the cooldown phase. So I want to point out there will not a combination of 0, 1, 1. Because if you have 1 at the second parameter, basically you mean you at the end of the first day you bought a stock. So if you bought a stock, you can't buy another stock because you have to sell the stock before you buy another stock. So basically there will be no such combination 0, 1, 1. So for 0, 1, 0 is basically the end of first day, you bought the stock, you are in cooldown, right? So for the DP000, which means that at the end of the first day, you have no stock, but you are in cooldown. So maybe because you bought and sold in the same day. And for DP001, at the end of the first day, you have no stock and you can still buy. Basically, it means that you didn't do anything on the first day. For the DP010, you have minus stock price, right? And for the other base cases, you have 0. So again, draw the recurrent tree. Draw the recurrent tree is very important. And then we have the recurrent tree, right? So in order to get the final result, we need the maximum between dpn-100 and dpn-101. And for dpn-100, how can we get here? Basically, we sell the stock on the last day, and then this will based on the optimal solution by the end of the previous day. You have 1 stock, right? And then for the dpn-101, now you are not in cooldown, you have no stock. Basically means that you rested on this day. And then it will based on what the optimal solution in the previous day. It's either a 0 stock not in cooldown or 0 stock in cooldown. Even though in the previous day you have 0, 0. And then after you rest on the last day, your cooldown will be over. Now you can still buy the stock. And then if we keeps going to the lower of the recurrent tree, we can actually find this recurrent relation, which will be also the transition function. For 0, 0, it comes from you are selling the stock on this day. And then it will be based on the optimal solution of having 1 stock in the previous day. And then for a 0-1 combination, it means that you don't have stock, but you can buy again. So you rested on this day, and then it will be based on the previous day. You either have the 0, 0 from previous day, or you have the 0, 1 from the previous day. And for a combination of 1, 0, basically means that you have 1 stock, you buy the stock on this day, and then it will based on no stock, no cooldown from the previous day. Or you just take a rest today and you will have 1 stock from the previous day. And then these will be the base cases for the top-down approach. You can recursively call, and then when the recursion stack pops, you will automatically build the DP table. And but we will just use the bottom-up approach as an example. So basically, we would from the base case build up a DP table directly to keep track of all the sub-problems until you reach the final answer. So again, you have 3 parameters: day, number of stock in account, and cooldown. 0 for can't buy and 1 for can still buy. And then this is a bottom-up approach written in Java. And these are the base cases. And at the end of day 0, you have one stock. So DP000 is at the end of day 0. You have 0 stock. And you can't buy. So it's because you buy and sell in the same day. And for DP001, it's the end of day 0 and you have 0 stock and you didn't do anything, you can still buy. And these are the transition functions for DPI00. It basically means that at the end of ith day, you have no stock, you are in cooldown. So basically means that you sold the stock today, right? Then it will be further based on the optimal solution of having the stock from the previous day. For DPI01, it means that you rested today, and it will be based on the optimal solution from the previous day. It's either I-100 or -101. So if it's 00 after the rest, the last parameter will become 1 again. So you can buy again. And for DPI10, it means that at the end of ith day, you have the stock, and then it either came from buying the stock today or rested today. For the final result, you are not sure at the end of the last day you are in cooldown or not. So you just take the maximum of DPN-100 and DPN-101, because the ultimate goal is to get the optimal solution at the end of the last day with 0 stock in your account. But we are just not sure if we sold the stocks prior to the second to the last day, on the second to the last day, on the last day. So again, very similar thought process, different parameters. We are trying to use parameters to track where we are in the recurrent tree and where we are in building the DP table. So here are a few key takeaways from this video. First of all, it's helpful to draw the recurrent tree for dynamic programming. So the recurrent tree can help you identify the key attributes for a problem to be solved with dynamic programming. And also at the same time, it will be helpful to identify the transition function between different states. So definitely, like for someone trying to grasp the dynamic programming, it's always helpful to draw the recurrent tree at the very beginning. And then there are 2 approaches for dynamic programming. It's regarding the information processing order. So the first is top-down. For top-down, you start from the final answer. You recursively call all the subproblems until you hit the base cases with the known information. And then the recurrent stack will pop. And then the return value will help you back calculate all the subproblems until you reach the final answer. And then it will automatically help you build the DP table to help you track all the optimal solutions to the subproblems. So this is the top down. And then for bottom up is basically you build directly from the base cases with the known information, and then you build up the DP table until you reach the final answer, the optimal solution to the problem. The similarity between the top down and bottom up is you both will need to build a memo or DP table to help you track the optimal solutions to the subproblems, and you will rely on the known information from the base cases to get the final optimal solution. And the difference is in the top-down approach, you will rely on a recurrent stack. First, you recursively call and build up the recurrent stack, and then the recurrent stack will start popping, and then it will automatically help you build the DP table. And the last point is, so for recursion, it will be helpful to define the parameters to help you track the state, basically where you are in the recurrent tree in the top-down approach, and where you are in building the DP table in the bottom-up approach. So I think someone also calls this thought process as the state machine. Basically, wherever you have a recurrent, you are trying to use some parameters to help you track where you are in the current tree or where you are in the process of building the DP table. So this way will make many problems much simpler to be perceived and to be solved. So this is the end of the video. So if you found this video helpful and you like this video, please consider subscribing, liking, or leaving a comment below how anything particular in this video is helpful, or if there's anything I can improve for future videos. And I also would greatly appreciate if you can consider buying me a coffee on Webmemo or YouTube if you find this video is helpful. And thank you so much for watching. I hope through today's video we are able to connect some dots, and cheers.